Okay, hi everyone. Thank you for coming. I am Takashi Ishida, and I'm a lecturer at the University of Tokyo and visiting scientist at RIKEN AIP. We have been hosting TrustML Young Scientists seminars, TrustML YSS, which is a seminar series that features young scientists giving talks and discoveries in relation with trustworthy machine learning, led by Jing Feng over here. And today is the 31st seminar, and it is a great pleasure for me to introduce our guest today, Sheng Liu. Sheng is a PhD student in the Center for Data Science at New York University. His research interests lie in general area of machine learning, particularly in robust deep learning with imperfect data sets, such as corrupted data, limited supervision, and small data, as well as their applications in medicine, such as Alzheimer's automatic detection. Sheng is also a member of the Math and Data group at New York University, where he works on inverse problems and optimization. Out of school, he loves playing tennis, scuba diving, surfing, and any water sports. So Sheng, we are very excited to learn about your research. And if you are ready, please begin.
Thank you, Dr. Takashi and Jinfeng for the invitation of the talk, and thanks Takashi for a very nice introduction. I'll start to share my screen and start the talk today. So first of all, I guess can you see my screen?
Oh, looks good. Thank you.
Okay. So today I'm going to talk about two problems, I'll say, like they're unified by a same perspective. One problem is what we call probability estimation, and another problem we call noisy label learning. And I'll start with a maybe more familiar topic to this crowd, that is noisy label learning. And then I'll talk about what is probability estimation problem, and then I'll talk about the similarity between these two problems from the early learning perspective. Please let me begin with noisy label learning. And a very naive or like a very simple toy example here is that we have a data set where there are 3 images. And the labels for them, for example, the first image is a fish, and the second image is a dog, labeled as dog, and the third image is labeled as dog, which is the wrong label. So the noisily labeled data set is a data set where there are certain part of examples are labeled correctly, and some examples are labeled incorrectly. And let's thinking about even more toy setting or idealized setting is that the wrong labels are assigned randomly. Basically, it's not dependent on the image itself. It just assigned randomly from different categories, but not the ground truth category. So here, it's possible that it's kind of randomly labeled as dog or fish. And it will not bias towards a specific category because it's not dependent on this specific input. And under this idealized setting, we run an experiment. Let's say we train a resident 18 on CIFAR 10, and well, 40% of labels are randomly flipped, as we discussed before. This is a very idealized setting. And what's gonna happen is that we want to see what is the model's prediction gonna be. And let's recall that for a noisily labeled data set, we have 2 parts of examples. One group is that the examples are correctly labeled. And another group is contains like examples that are wrongly labeled. And let's first focus on the examples with clean labels or correctly labeled. And this figure basically showing that, okay, the x-axis is the epoch of training. Basically, it shows that the iteration of training. And from left to right, we're training the model longer and longer. And the y-axis is actually showing the fraction of examples. Well, the fraction of examples. So here the green line basically showing that the fraction of examples that the model predicted correctly. It's not surprised that the model will keep predicting correctly when it's training on the clean labels, right? Because the model is overfit. It's a training, it's a graph on the training set. And because the model is training on the clean labels, it's not surprising that the model is gonna fit the clean or the correct labels. That's why you'll see the growth or increasing of the green line here. And we'll see the decreasing of the blue line over here. This is not a surprise, and it should happen in that way. Otherwise, we're not training the model correctly. But a more interesting part is that how about the examples with wrong labels? What is going on for them? A very naive thought is gonna be because the models are trained on the wrong labels for those examples. It's very natural to think that, okay, a similar graph will look just opposite of this. That means that the green line will be the blue line here. That means because the model is training on the wrongly labeled examples, so more and more for those examples will predict wrongly. So you'll see that the correct examples will be the blue line here, and the green line will be the blue line. The blue line will be the green line. That's what we like a very initial thoughts about this. But this is not exactly what happened. What happened is more complicated and or more interesting than that. Is that we will observe like two stage that we call one stage as early learning and one stage as memorization. As you see the green line here, instead of directly going down, it will first going up and then going down, instead of directly going down. What does going up mean? Going up basically means that even those examples are wrongly labeled, they can still be predicted correctly. Okay, that's why you see a going up. That's basically saying those examples, even though they're wrongly labeled, they can still be predicted correctly. And then you'll see a going down as we were expected in the previous slides, right? And we'll see that the blue line, the blue line, the red line here is basically showing that the model, how many examples are predicted as the labels. Remember here, the labels are wrong. You'll see because the model is training on those wrong labels, eventually will goes up very high because the model is trained on those wrong labels. But in the very beginning, still it stays low. Instead of directly grow directly up to a very high position. It forms as S shape. Basically, it's like first be a very slowly overfit or like slowly fit the wrong labels, and then it will increasing and then eventually overfit the incorrect labels. So this is what we call the memorization stage in the later stage of training. But in the very beginning, you'll observe what we call early learning stage, that the model, even the model is trained on wrongly example or wrongly labeled example, it still can predict it correctly. You'll see the growth here. And that's what we call the early learning stage. And let's remember this concept and talk about like how we kind of trying to model the label noise problem. And let's think about this problem. This problem is that let's assume that we have a model F with the oracle parameters. And the oracle parameters basically this model saying this model can always predict correctly. So give a cat image, a predicting cat, give a fish image, a predicting fish, and dog image predicting as a dog. And then what does the noise label here? Generated from like a model that predicting correctly plus some actual term as star, we call it label noise, to basically flip the label. let's say. So let's think about this F as a vector, like a one-hot vector indicating the ground. Let's say the X here is a fish image, okay? And the F here is gonna be a vector, like a one-hot vector indicating that the fish, okay? So let's say we have three class, dog, fish, and the cat. So it's gonna be 0, 1, 2 for different categories. And this one will always predict fish. That's gonna be class 1. So it's gonna be a one hot vector with 0, 1, 0. And the label noise is actually gonna be not noisify the original prediction. What's that gonna be? It's gonna be a one entry with a -1 and a one entry with a 1 to flip the original prediction. And the rest entries are 0. So as you might think about, think of this as it's gonna be a noisy, it's gonna be a label noise, and it's gonna be a sparse vector. And the noise label is for sure is also one hot vector if we think in that way. Okay, let's simplify everything. And let's recall some classic robust learning, like in the past in compressed sensing and like in statistical learning. When we trying to solve this problem when S is sparse, right? And we have a how can we recover the ground truth oracle parameter? We use a L1 distance or L1 loss to recover the ground truth signal from the noisy signal. That is like very popular in the past literature, like maybe before deep learning even, right? In compressed sensing, for example. If we assume some like specific like property of the model, we can use this L1 norm to recover the clean signal from the noisy one. However, there's a very obvious problem here. That is the global solution is still the one that F equals to Y. Y is here, for example, Y here is the noisy label. Forgive me, I forgot to add a I here to indicate the ice example. So the global solution, that means that the solution that makes this whole loss function to be 0 is when F equals to Y. And this is still the one that this model overfit to noisy labels. And this is not desirable. But we still observe some literature that using the L1 and observe some improvement on the label noise problem. But you can imagine that if you train long enough, it will eventually, at least on the training set, to overfit to the noisy labels. And our approach that we kind of published in ICML this year is that we use a sparse over-parameterization term. We call it a sparse over-parameterization approach. Instead of directly using the L1 loss function, we kind of expect we kind of using the actual term that we call the sparse over-parameterization term here. UI squared minus VI squared. I'll talk about it later. What are this? To model the label noise term, the label noise, which is, for example, in a very simple setting, is -1 and 1, and the rest are 0, like a vector like that. And we want to learn this U and V to approximate the label noise S I star. And how does this happen? At least before I talking about the whole process, we see a ideal solution is that when the UI square minus Y square converge to the label noise Si, and when the F, the model converges to Oracle, a model with the Oracle parameter, it's gonna be one of the solution at least, right? Because that's how we generate Yi, or how the Y was modeled. And why does that happen is also rely on early learning, because in the early stage, as I said, even though the model, the data, they are part of the data set are wrongly labeled, the F can still predict correctly for those examples. And when the F predict correctly in the early learning stage, then the F is very close to the Oracle model, right? And at that case, if we were trying to learn the U and V, U square minus V square, it's gonna sort of like approximate the label noise. And that's how it happened. That's first the like why it kind of happened in the intuitive explanation. And we should also observe another phenomenon is that is only one global solution. There are other global solutions exist. For example, when the U square minus Y square equals 0, basically it doesn't play any role, right? It doesn't play any role in the whole equation. Then the F is still equals to Yi. In that case, the F is still all fit to the noisy label. Yi here is noisy label, right? So how we make sure that, okay, we take advantage of the early learning stage and we use the F here that can converge to the Oracle model, and the U square and minus V square will converge to the noise S star. That is basically relied on optimization algorithm, because we know that there are many global solutions exist, and the optimization algorithm will lead to only one. Okay, if we fix the algorithm, and by fixing algorithm, basically we mean that, okay, one, we want to fix the initialization. And the second, we want to fix the learning rate and the optimization, like either SGD or gradient descent or something, to make sure it converges to one of the global solution. And that's actually what we did. We realized that actually there are a very simple solution or simple bias of gradient descent. We're just using gradient descent, and we choose the optimization algorithm as gradient descent, and we initialize the U and V to be very small. So here the U and V is a very small value. We initialize as a normal distribution. Like the normal distribution is with a mean 0 and a standard deviation 1 minus 16. And in that case, you'll observe that if we run a gradient descent and the learning rate is very small for U and V, remember that here we have like two parts to optimize, as I said in this loss function. The first part is that the U and V, we need to optimize it. We alternate between, and the second part is the original model parameter. We alternate between them. The first step is to optimize the model, and the second step is to optimize the U and V. Okay. And the U and V, we realize that, okay, we need to initialize them to be a very small value, very close to 0. And the second thing is that we want to make sure that the learning rate for U and V are very small. So that's why we added alpha to control the learning rate from the original learning rate of the model parameters. And in that case, we realized that, okay, this U square minus V square will be approximate S, and it will be a sparse vector. And the reason why we want this form of the term is because we want a sparse vector. As I said, this vector should be something like a 1 and -1, and the rest are 0. Something very close to 0 for the rest of the entry, and for the main the main entry is just what we care is the ground truth class entry and the wrong class entry. We just need to flip those two entries, and the rest we don't need to care about them. And that's why we want this form, because this form, as you can imagine or think of it as a factorization of a sparse vector. So the reason for why we use this kind of form is that we know, like of some prior knowledge, that this S is a noise vector, is a sparse vector. And regarding the results, it achieved very good results. And because it's kind of for each example, we have this kind of term to model the noise. So it kind of achieve also good result on the instance or the input depend label noise as well. Okay, this is basically the noisy label part, and now I'll skip a more I will go to more of the probability estimation problem. Before that, I'm wondering if there are any question or if no, I'm just going to the next part. Okay. Okay, it looks like we don't have any questions, so I'll go to the probability estimation part and then explain, first of all, what is probability estimation problem, and then why and how does early learning happen in this problem. Yeah. So what is probability estimation here? The probability estimation problem is that, for example, when in real life applications in many different settings, we know that, for example, yeah, kind of hear some noise, maybe. Okay. Yeah, we want to estimate the probability of events. For example, like if we want to use a radar map to predict the possibility of raining, because we are not for sure that it's gonna rain or not, right? Forever, because there are a lot of events with intrinsic uncertainty. For example, we want to predict whether the modality of a patient, even though he or she they might get some cancer or something, but still like the probability of the death is gonna the outcome is gonna be either they die or not, but still by using like a medical imaging, we want to predict death of that subject, but that does still have some that kind of outcome still have some like intrinsic uncertainty. And the goal here is that we want to estimate probability of uncertain events from high dimensional inputs. That's why we use deep learning here. For example, images and videos. And this kind of problem is not equivalent to classification, because classification, we are always trying to predict the person will die or not, basically the outcome, but that is sometimes not very interesting. We want to predict is that what we are actually interested is the probability of the death or the probability of raining, right? Instead of, okay, it's gonna rain or not, sometimes it's especially for those uncertainty events. So remember here, we are this problem is not equivalent to classification, but in real life, we only know the outcome. We only know like, okay, by giving the radar map, we know that, okay, it's rain or not. We don't know the probability. We don't have the ground truth probability. We only have the outcome labels. Basically, okay, it's raining today or it's not raining today. We don't know the probability for sure. And for like a subject, like the modality of a patient, we know that whether this patient is die or not in the end, but we don't know in the very beginning what is the possibility or probability of the modality happen. That's the trigger part, the intriguing part, also the difficult part of this kind of problem. Here is a very simple example. Here we see his pathology images, and we want to train a neural network to estimate what is, given this medical imaging, we want to estimate what is the probability of this patient survive. And we know that, for example, if, as I said before, that we kind of don't observe this probability. Let's say it has a ground truth probability, but just we don't know it. The survival probability given this histopathology image is 70%, but we never observe it. but we observe the outcome is that this patient died. Okay, so the outcome is death. And while training, we only have access to this input, okay, input image and the death, which is the outcome of the event. But we don't have this probability during this probability during training, and anytime in real life as well. It's very difficult to obtain them. Then as we see, if we only have the input image and the output y, the y is gonna be one hot, or like 0, 1, basically. It's gonna be either die or not die, okay, or survive. So it's just 0, 1. Let's think about give another example, is that we want to use a image, okay, of like a face image of a person, and we want to use that image to estimate the probability of this subject facing some health risk or something like that. And we kind of simulate this data set, because in such a way we have the ground truth probability. Otherwise, it's very difficult to do analysis. So we simulate this data set, and then I'll talk about some real world data set as well. For simulating, how we do is that we know the input image and we know the age, which is 20. And we do a very simple thing, is that we say the probability of this risk happen is just the age divided by 100. So if the age is 20 for this guy, then probability, ground truth probability is 0.2. And then y is that we sample from the Bernoulli distribution, well, the probability is 0.2 and the outcome is 0. Of course, if you sample again, it's possible it's gonna be 1, because after all, like there are still probability that the outcome is 1, but we sample once here. We sample once and we got 0. And for 70-year-old lady here, the probability is gonna be 0.7, and then we sample once, say the outcome is 1. So the labels are, you can think of sampled from using the ground truth probability. And while training, we only observe the xi and yi, and we don't observe the pi. So if we use the cross entropy loss to train on this problem, we know that the standard cross entropy loss is a proper scoring rule. Basically means that if we are trying to minimize the cross entropy, the prediction of the model will be calibrated. Basically, it means that it will not overfit to 0 and 1s, the probability, outcome probability, but it requires us to have infinite many data, or like we can keep resampling yi from this ground truth probability. Let's think about the case that we can always resample the y from the using the pi. That means that we already have access to pi, right? Then we always resampling and get the new y during training. And it's not a surprise that a model will not overfit to this 0 and 1s. However, in the real life setting, we only have, just for each individual, for each subject, we only have one outcome. It's not possible to let it survive again and then run another experiments to get another outcome or something like that. So we don't have infinite many data. We also cannot keep resample the labels. So what we can do, before I talk about what we can do, is that, like, here is some graph that are trying to show you that, okay, if we have infinite many data, basically means that, for example, we can resample the labels during training. What's gonna happen is that the predicted probability of the deep neural network is consistent with the ground truth probability. It's not surprising, right? And here, is also another graph that's showing the observed frequency is also in line with the predict probability. So what?
Yeah, a question here.
Yeah.
So infinite data means infinite hard labels, and the images at X itself is finite, right?
Yes. In this experiments, yes.
How many images do we have in this experiment?
It's same as the as this data set. I think it's 10,000 or something. Yeah, it's not very small, but like, yeah.
Okay. Thank you very much.
Yeah. So yeah, so if we have only finite many example, that means it's more realistic setting that we have we cannot resample the labels. Basically, we see a significant overfitting. Basically means that, as you see that here, the predicted probability is concentrated on either 0 and 1. This is not surprising because the training labels are 0 and 1s, right? And you are training the model to overfit to 0 and 1s if you train long enough. And it's gonna be the predicted probability after softmax, it's gonna be 0 and 1 to perfectly fit the training set to perfectly reduce the training loss to 0, right? Because of the cross entropy, you require the probability to be very close to 0, either 0 or 1, to make it the loss equal to 0. And what we observe is that early stopping, by early stopping, you'll see a more or less similar figure to infinite data, but of course it's not perfect. You'll see that the predict probability is more or less aligned with the ground truth probability. And here is basically what we call early stopping or early learning stage, because early stopping is stopped at the early learning stage. So the early learning stage is not just, okay, the model predict correctly for the wrongly labeled example, or predict correctly or not correctly. The early learning stage can also be calibrated. The probability or the predicted probability can be calibrated. That means, okay, it's not overfit to 0 and 1s, and it's consistent with the ground truth probability in this case. Yeah, of course, it's not perfect. I see it's still like have something here, because this early stopping we are done is gonna be it's actually stopped by using a validation set. As you can imagine, okay, a model that perfectly fitting the training set at like 0 and 1s, it cannot be very good for the validation set. Why? Because the validation labels are also the underlying process of generating, let's think of it that way. The underlying process of generating the validation labels are also sampled just once based on the probability, the ground truth probability. So it's just a sample process and just sample once. So there's no reason that overfitting to the infinite data, overfitting to the training set will result in generalization in the validation set. So here is early stopping. Okay, and what we want to improve further is that instead of just do our early stopping based on validation set, we want to do more. We want, as we kind of do it in noisy label as well, we want to take advantage of the effect of the early learning and keep the model learning more. So that is a goal. The goal is that, okay, we can improve model that basically means that improve the cross entropy loss to minimize the cross entropy loss, and at the same time we want the model to remain calibrated. That is what we call calibrated probability estimation. The idea is very, very simple. Is the first step is that we want to use a cross entropy loss and train until the memorization begins, and instead of do early stop, right? We don't do early stop, and instead we alternate between enforcing the calibration at the same time minimize the cross entropy, and enforcing calibration realized on using the prediction of the model in the early learning stage to maintain that the model probability not goes to the two extreme that is 0 and 1s. And as you can see here, the training loss, if we just use a cross entropy minimization, the training loss will keep going down. This is not a surprise, and that makes the probability going to 0 or 1s. And if we start the cape, you'll see that the training loss stop decreasing further too much. And the validation loss, as I said before, there's no guarantee for generalization at all. So that what you will observe is that if you just do a cross entropy minimization forever long, you observe that increase in the validation loss. And then if you do cape, then the validation loss can be further decreased a little bit instead of like goes up to the rocking high place. And here is a similar graph as I showed before, but with cape. With cape, you'll observe something that better than early stopping. You'll see that this cloud is not as wide, especially here is not as wide as the early stopping, and especially on this figure as well. You'll see it's closer to the y equals x line here than the early stopping. So the cape actually helps more and improve more from the early learning, from the early stopping strategy. And here are some real world problem I want to mention. For example, in weather forecasting, we use this radar map of a region. We want to use this radar map to predict, okay, whether the rain will, whether it will rain or not, or like what is the probability of raining. And for collision prediction, we want to use this kind of dashboard video. We want to use this dashboard video to see, okay, whether in the next few frames or in the future, this car will have a collision. We'll have a car collision. And as we also discussed, like raised up in the very beginning as an example, is that this histopathology image, we want to predict the probability of a patient that will die in 5 years. So it's actually a very practically useful problem from this point of view. Is that for this problem, we care less about whether it's rain or not. We care more about to get a more specific probability about the rain will happen or not, because these events, it's not a certain event. It's not like a dog is always a dog. A cat is always a cat. It's 100% sure from that image. We want estimate the probability, and we care about the intrinsic uncertainty of those events. And here is the results, and we use a Brier score to estimate the to report the results, and the Brier score is just the MSE. I'll say the MSE between the probability and the the Brier score is just the probability between is just the L2 distance between the predicted probability and the outcome, the actual outcome. The L2 norm sum over all the examples, and it's actually widely used in calibration problems. And what we kind of observe is that we consider these 3 real-world data set, and we also consider a lot of calibration method, like methods specifically designed for calibration. But I need to maybe talk about, like in the very beginning, that this problem is not as same as calibration. Calibration is just require that, okay, if you report that the probability for example, in classification, the probability is 0.8 it to be a dog. It's not about like this image has 80% of possibility to be a dog. It's for sure it's a dog. It's just like for the 80% of the examples that labeled as dog is predicting correctly. So it's a different problem. But we can also imagine that those calibration calibration method will prevent the prediction from collapse to 0 and 1s. So that's why we want to compare with them as well. And actually, this paper is actually the first, I'll say, like, as far as our knowledge, is the first one that actually trying to research on or like focus on this probability estimation problem. And for the calibration problem, they have many methods like focal loss, for example, and they to prevent it goes to 0 and 1s. And they have like, for example, the very Varina ones that we mentioned before is early stopping. They have temperature rescaling, right? And entropy regularization, basically to I think increase the entropy of the final prediction to prevent it goes to 0 and 1s to make the prediction more uniform. Our methods actually, you can see there are two versions. I want to like describe like too detail about like these two versions, but the CAPE method that takes advantage of the early learning stage where the model is calibrated and use that model's output to further training the model, achieve a very good result on these three data sets. And in conclusion, we see that deep neural network can be effective for probability estimation problems. It's just we don't want it to just train on the 0-1 outcome labels too long, because it will eventually overfit. Because it's over-parameterized and the networks are powerful, it will eventually overfit to those 0 and 1s. And the second thing is that we can exploit early learning to enforcing calibration. And the early learning is not just, it can predict correctly for those wrong labeled examples, or it can predict correctly or not correctly, because correctly is not care about probability. It's just care about whether the max probability is consistent with the ground truth class or not. And here we don't focus about the classification problem. We focus on a probability estimation problem, and we realize that the probability in the very early stage can be calibrated, and this can improve probability estimation problem as well. And the third need, or like very interesting maybe future direction, is that of course more methodology on this problem, because this problem is actually really important in practice, in real life. We can invent more methodologies and to solve this problem, because this problem is actually difficult, surprisingly, because we don't have the ground truth probability, we only have the outcome labels. And we also need more benchmark data sets. In this paper, we kind of propose one simulated data set that is very naively or simply simulated. We kind of use age to generate the risk, and which is very simple. And we have 3 data sets that is we collected from the real world, and we have a very small part of it well, the we don't know the probability. We only know the outcome of the event. And I think that's pretty much for today's presentation. Please let me know like if you have any questions, or like you're interested in any part of the talk or anything.